Hello and welcome to part 2 of lesson number 1 in Unit 2A, Quadratic Functions, Forms and Transformations in our grade 11 University College math class. This is analyzing quadratic functions. In the first part of this video, we went over how to distinguish linear and quadratic functions using differences, first and second differences, to distinguish between the two of them. We went on to look at how equations, viewing an equation, can help you distinguish between linear and quadratic functions by using the degree. And degree is represented by the largest exponent on any of the variables in the equation. We went over that for linear and quadratic functions. We reviewed some of the terminology we'll be using with quadratics, including direction of opening, vertex, and how to find the vertex in one particular form, which is called vertex form, and also the axis of symmetry. So we're going to jump right in with the example number 3, and we're going to get to apply some of these things. So here we have a table of values, 0, 0, 135, 260, etc. I'm going to zoom out here a little bit so you can see the actual graph. I've just provided a bit of a scale on it. Again, you can do your own scale. Maybe copy it down now, and that way you're working from the same set of pieces as I am. I'm going to start graphing it. So we have point 0, 0. There's 0, 0. Point 1 is at 35, so that's about here. Point 2 is at 60, which is about here. Point 3 is about 75, which is here. Point 4 is at 80. And then the pattern just repeats down the other side. And I'm just putting those points in now and ending at 8, 0. All right, so now I'm going to sketch through this. Again, we weren't given an equation for this, but I think it's modeling time and height for something. So we have some points, and I think we can assume that although those are the points that were provided in our table of values, there will also be a height for all those little intermediate pieces as well. Okie doke. So there's our graph. We're going to calculate first and second differences in order to determine what kind of function this is. Obviously, by looking at it, we know that this isn't going to be a straight line. And, you know, actually, let's just skip first and second differences. Let's skip it right here. We know how to do that. Just waste a little bit of time. I think visually here we can see if we only had the table, then for sure we would go for it. Because we've sketched it, I think it's obvious what it is. This type of function is a quadratic. It's got that right shape. And we can also see that repeating pattern here in the tables where you have opposite points that match, zeros, 35s, 60s, 75s, and then that unique point right there. So the direction of opening is going to be down. Obviously our parabola is opening down, meaning that the opening to the parabola, if you were to consider that it has sort of like, I guess, a mouth or like an opening, it's at the bottom, so it's going to be opening in the downwards direction. State the direction of opening is down. State the vertex. So the vertex by inspection is the highest point. We can see it right there. It's at the highest y component, or output component, is 80, so that's going to be 4 and 80. Now remember here, the vertex is a point, so it needs to be written like a point. You can't just write down 80 or like 480 with no brackets. It has to show up like an ordered pair. So is the vertex a maximum or a minimum? Well, is 80 the highest point or the lowest point? It's the highest point, so that's going to make this a maximum. Give the equation of the axis of symmetry. Okay, so let's sketch this on. We talked about that briefly right at the end of the last video, but I'm going to sketch it in. The axis of symmetry actually goes right through the vertex, and it's a vertical line that gets sketched through your vertex and all the way from the top of your grid down to the bottom of your grid. And it needs a label, and it's an artificial x-axis that we've sort of put in here. I know it seems silly, a little bit hard to understand, I guess. Because obviously the vertical axes tend to be y's. However, this is more like, maybe an axis isn't the right word, maybe it's more like an equation, where we're talking about what is the equation of the axis of symmetry. Vertical lines have an equation that starts with x. They only have an x value that is one value, no matter what the y value is. And in this case, our x value is, as we can see at the bottom, going to be 4, which is the x component of the vertex. So there is our axis of symmetry. And let's state it. X equals 4. Has to be an equation. Again, it's the equation of the axis of symmetry. So it's not just 4. It's an equation, x equals 4. Now let's look at the range of this function. So recall that the range is the vertical or y components that work for this function. If you could imagine, we're going to take all of the points that we have here on our graph and we can just sort of like mush them over onto the y-axis. So if I were to do that, I would get, well, 80s on there for sure, and then all these little points in between going down to all the way down here to 0. So if we just look at this as if it's that number line from the lesson that we learned, domain and range, in Unit 1, if we look at that, we would see, all right, so here's the range. It starts at 0 and goes to 80, and it's continuous. We can see that because it's a continuous line. So let's write this out. So we would say set of all y such that y is an element of, so continuous line, real numbers. So the low point is 0. We're dealing with y. The high point is 80. There's our set. So we know this is going to be less than or equal to 80, and at the same time less than or equal to y. There we go. So we reach both of these values, which is awesome. Again, those are closed dots that we put over here. So that is our range, and this is a real world function. When I say that, what I mean is that our parabola isn't going to continue down forever and ever and ever. We're talking about as time passes, the height of something. So if it's at a height of 0 at time 0 and time 8, in theory it's not going to go into the ground, I guess, unless maybe we're talking about like an asteroid or something. I'm not sure. In any case, based on the information that we have not just a high limit, but also a low limit as well. So there you go. There's a worked example. Let's jump down here into domain and range revisited. So linear functions, as we learned at the end of, I think it was the lesson that we did at the end of Unit 1, was the domain is always for straight lines going to be wide open, meaning there's no limits. The set of all x such that x is an element of real numbers. The range will also be set of all y such that y is an element of real numbers, no limits. These straight lines, they just go on forever. There are, however, two exceptions. One of them is vertical lines and one of them is horizontal lines. So if we look here, let's imagine we have a vertical line, and I will just sort of sketch this out. So here it is. So we have x equals 5, and so that's like, say, over here somewhere. So here is our vertical line going up and down forever and ever and ever. This equation is x equals 5. So what is the domain going to be? Interestingly enough, there's only one x value that works for this particular function, and that's x equals 5. It doesn't go left and right. If you were to take all this and squish it all down onto the x-axis, you would literally just have one point, and it would be at x equals 5. So we should set the domain appropriately. Set of all x such that x is an element of, now again, real numbers is true, but it's way too broad. Even integers might be too broad here, although I wouldn't go much more specific than integers if you didn't have to, but this is actually not even just a whole number, but also a natural number. It's a positive 5. We're going to stick with integers, but realize that really anything more specific than real numbers would be enough for me. And again, we just have that one value for x, which is 5. The range, on the other hand, if you can imagine taking this and now squishing it all over onto the y-axis, just like push the whole line, this is really going to go forever and ever in both directions. So we should model this continuous line in our range by saying set of all y, such that y is an element, continuous line of real numbers, no limits. This thing's going to go up and down forever. So that is an exception. Now this vertical line, interestingly enough, just as a point of fact, is the one and only straight line that is not a function. Because as you can imagine, if I were to draw a vertical line through x equals 5, I would hit the function infinite times, which means that it's not a function. Let's have a look at example 2 of the exceptions, which is a horizontal line. So horizontal line, I'll just do a little sketch of it here. So here's our grid. So here's y equals -2. That's down here underneath, and it's going to go off forever in both directions. That's y equals -2. So what does that mean for us? Well, again, if we're talking about the domain, as you can see, if we were to push this whole thing up against the x-axis, it would just go forever and ever in both directions. We'd squish it up it would map perfectly over here in both directions, a continuous line going forever. So we would articulate that as the set of all x, such that x is an element of real numbers with no limits. It's going to go on forever and ever. Range is where we get to see a little bit of a difference. Again, if you can imagine squishing all of this up against the y-axis, all of this would just mush into this like singular point right here at -2. So again, we'd want to reflect that here in our range. We'd want to say the set of all y such that y is an element of, now this time we would need to use integers because it is a negative number. However, real numbers to me is it's too broad. We should be as specific as possible because the one and only y value that we have is -2. So there you go. That's the domain and range of two exceptions when you're working with straight lines. Otherwise, wide open. No limits on the domain, no limits on the range. Let's jump over to quadratics. Quadratics are nice too because the domain is always going to be wide open. No limits on the domain. Again, those are the x components, right? And if you can think about a parabola that opens down or opens up, it's going to go left and right for eternity, so it's going to fill that up. The range, however, is always limited by the vertex. And I'm just going to write that down because it's a nice, it's a nice little summary. It's always going to be limited by the vertex because the vertex is the turnaround point. So we need to know what the vertex is in order to determine the range. Now there's a little blurb here that says if the equation is in vertex form, that is y equals, and this will be new as I said for some of you, this is vertex form. We're going to really dig into this in the next lesson. But this is y equals a bracket x minus h all squared plus k. The h and k components, those are the parts that correspond to our vertex. Specifically in terms of height, that's going to be our k value. So you use the vertex and the direction of opening to determine the range. If the equation is in standard form, we're going to skip that just because that is a bit of a cheat. We're not just going to do that now. We'll do that when it actually shows up in the actual, in the forms portion of the unit. So last thing I want to do here, we'll stop this and then we'll do the last 3 examples in a new video, or in a new part of this video. But if you can imagine here you have it. Here's our parabola opening up from the vertex. We know that the range then, if we were to mush it all over to the side, the range would be equal to whatever your vertex is and going up to infinity. Similarly, if it was another slightly different version of that parabola where here's your vertex, but instead of opening up, it opens down. Again, what you would have here as your range, if you mushed it all against the y-axis, it would be point of your vertex and all the way down to infinity. So knowing both vertex and direction of opening, that's the essential stuff that you need in order to determine specifically the range of a quadratic function. So this is the end of the second part of this video. The third part, we'll tackle 3 more examples and then we'll get you off to your homework. So we'll see you in part 3.